we manage. Okay. So, now we're going to introduce the topic of hearing and speech. Okay. So first of all, I would like to ask you if you're familiar, for instance, with the ear. If you know a little bit about the ear, do you have any knowledge, any little knowledge, a little bit? Yeah, some people say yes, some say no. Okay, so we'll tell you a little bit how the ear is done, okay? Just to give you an example of how our sensors are able to capture information about the external world. So this is your ear, and the external part of your ear is called outer ear, okay? And this is literally your ear, like called pinna. And then you have the external auditory canal, which kind of directs all the sounds coming from the outside into the inside of your ear, okay? What is there in the inside of your ear? Well, first of all, I would like to ask you something. So let me try to put my video on again and see if everything crashes. Maybe now it's gonna work. Yes, okay, good, I'm back, awesome. So what I would like to ask you is a very simple question, but it's very tricky. So the question is the following. What is the sound?
The vibration of the air.
Vibration of the air. Okay, that sounds like a good answer, right? Now, what do you mean exactly by the air vibrating? Oh,
well, the sound creates waves by moving the molecules of the air, which then make the impact on the membrane and air.
Wait. You're going too far, okay? You're going too far. And I'm crashing. Disappearing. Stop video. Sorry about this. Okay, I'm slowly coming back. Okay, so sorry. Let's make one step back. Okay, ignore about what we do with the sound. I'm just asking you guys what the sound is, right? And you answered vibration in the air, and that's actually a good answer. But I'm I'm wondering, how does the air vibrate? Like the air is composed by molecule of oxygen and other gases, like I don't know, whatever. It's called azote in Italian. I don't remember the name. Nitrogen. Yeah, that's the name. Right. So how does this air vibrate, right? So I guess the molecules somehow vibrate, but can you tell me a little bit more about this? Or can I have sorry, I don't see your names, but someone raised their hand, right? Can you say something?
Unmuted, yep. I'd say it's actually
Mario.
pressure waves. Yeah.
Yes.
So the sound waves are pressure waves through. So it's a domino effect, and you have high and low pressure areas. And what the waves consist of. So the highs and lows of those waves are actually high and low pressure.
Right. So thanks. So you're giving one more information, right? So, oh my God, why aren't your names? Oh, it's so confusing. Okay, whatever. Veronica, is that your name? Alice. Sorry, I'm really bad with names. So Alice said that the air vibrates somehow, and this vibration can be sort of captured into a waveform, right? And Mario said that it's actually, this vibration is caused by pressure, right? In particular, by variation in pressures. And then you have this kind of domino effect where particles of air vary their pressure and they're going to transmit this information to other particles of air. And that's why if I'm here, I can hear you speaking if you're 20 meters away from me, right? Now, my question is there any physical phenomenon that give us an idea of how these things work? To make a nice example. Do you have anything in mind? Yeah.
Are you maybe referring to electrical signals, which also have ups and downs and
yeah, no, it's a very
kind of a weight?
No, it's a very dumb question, mine. So it's like, you know, can you think about some phenomenon in the nature where you have these kind of things of waves that are sort of expanding from a center where the generator of the phenomenon is created?
Yeah, like in a pond or water.
Obviously, water.
Bingo! That's exactly what I wanted to hear. So when you toss a rock in the water, right, you see these kind of things of waves spreading from the point in which the rock touched the water, right? Well, sound is exactly the same kind of phenomenon. So you have a generator, you have a source of this perturbation, and then the perturbation expands and diffuses in the medium, which for the sound is air, right? But for a rock in the water is water. But the principle is exactly the same, right? So this constant compression and extension in the pressure of air is basically somehow gonna provide you the information about who's talking, what is this person saying, what kind of pitch, whether this person has a high tone pitch or low tone pitch, and yada, 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 okay? So the question is how this happens, right? How are we gonna translate variation of pressure into sounds? That it's not clear how we can have a one-to-one mapping of this, right? So I'm gonna try to give you an answer, and the answer is this. This big ear here is just basically capturing these waves, right? These waves due to the continuous variation of pressure, and channeling these waves into your auditory canal, which is literally the inner part of your ear that sometimes you might clean in the morning, right? And then if you go further down, you get to this point, which is called middle ear, which is very important. And this includes 3 bones. These guys are bones, okay? If you break these bones, you're gonna be in big trouble, meaning that you're gonna lose the ability of hearing from one ear, okay? These bones are called malleus, incus, and stapes. And they are just gears. They're basically gears that have a very important function, which is to amplify the variation in the air and to transmit it to a different medium, which is water, okay? Where is the water? The water is in your inner ear. So these little things just work like the membrane of a microphone in a way, and they convert information. It's actually the kind of information because it's variation in pressure of the air to variation in pressure of the water, okay? Now, why do we have water? Well, we have water because the most important part of your inner ear, which is the cochlea, the real microphone in your ear, right, is gonna work in water because of its physical properties. And we are gonna see how it works. So yes, sound is an oscillation, waves, vibration of pressure. All things that you said. So great job, Alice and Mario. So you got air, and then these vibrations are turned from air vibration to water vibration. Nothing really fancy at this point, right? But the magic happens in the cochlea. The cochlea is a transductor, right? How is it made? It's basically a membrane, right, that contains some very, very tiny, they're called hair cells because they really look like hair, okay? So what happens is just right, your speakers vibrate when they emit sounds. This membrane induces some mechanical movement on the hair cells on it, right? So the membrane vibrates because of the sound. It makes this little hair move. And when these hair move, they induce a flow of ions to some stretch-sensitive ion channels. Now, you should know what ion channels are, right? And you know that when ion channels activate, they change the voltage of the cell. These ion channels are activated by the movement of the membrane. And then, bang, the magic happens, meaning that these little hair cells initiate neural activity, right? And you know a little bit how it works. The ion channels generate an electric charge. This charge, if it's strong enough, is going to trigger the release of neurotransmitters, and the neurotransmitters will initiate a potential, right? This is not an action potential because there is no axon bringing information. It's a postsynaptic potential, okay? So this information about the vibration of the sound is captured by this little hair and it's transmitted to other parts of the brain that we are going to see in a moment. Good. The second important thing about the cochlea is that you can see it has this tonotopic structure. So we encountered somatotopy structure, right? The somatotopy of the homunculus, where you have the representation of your body parts on your sensorial cortex. Now we're going to talk about tonotopic representations, which basically mean that you map on a bidimensional or one-dimensional space, right? Like your cochlea, you map tonal properties of the sound. And the tonal properties of the sound are about the pitch. And we are going to see what this is in a second, okay? So basically, all that happens is that you have air is converted into, is amplified, the air vibration, and is transmitted to water vibration. This water is going to vibrate in your cochlea, and this vibration of the water make the membrane attached to these little stringy cells move, stretch back and forth. This is initiating a neural activity by flow of ions, which are going to cause the release of neurotransmitters, which is going to cause a signal coming from your cochlea being transmitted through your nerve to the rest of the brain. In particular, it's going to go to your dorsal cochlear nucleus, right? Where you have all the bodies of the neurons receiving the signal from the cochlea. And these are going to retransmit the signal to your superior olivary nucleus, which is a very old part of the brain important for sound processing and sound localization. Then it's going to go to your inferior colliculus, which is also important for sound localization. And that's going to retransmit the information to your medial geniculate nucleus, which is in the thalamus. This is the thalamus, right? Which, as I told you last time, is basically retransmitting the information to the auditory cortex. Now, why do we have all these steps of transmitting information? Because at every step, you're not just retransmitting some certain information, but you are elaborating it at some point, okay? For instance, sound localization is already done in the thalamus. So the cortex is going to do some additional high-level analysis. Right, so it's interesting to see how many neurons are dealing with this information. So the interesting part is that the more you go upwards and the more neurons you're going to have. So you have 90,000 neurons here, then you're going to have 500,000 thalamic neurons, and then you get 100 million cortical neurons, okay? So you see why the elaboration of the signal is way more sophisticated in the cortex, because you have way more neurons dealing with that, okay? Now, if you look at your primary auditory cortex, which is called Heschel gyrus, which is this little orange part here, just like it happened with the somatosensory cortex, you have a map directly in the neurons of the cortex. And this map is tonotopic. So these neurons here are responding to sounds at about 300 hertz. These neurons here are responding to sounds at 900 hertz. And these neurons here, on one side and the other, respond to sounds at 3000 hertz, okay? So let's take a break a second, maybe. No, let's do it later. Sorry. Yeah, so central region respond to lower frequencies and outer region to higher frequencies, okay? And this, again, is called A1, or primary auditory cortex, the Heschel gyrus. But then you see that as you move away from that, you have a core area and a belt area, and also a parabelt area, right? So these are all primary, secondary, and higher level cortices. And you see that what is called the parabelt area is actually overlapping with this region, which is basically encompassing Wernicke's region, right? So we're talking about sound, but we are entering into comprehension territory at some point, right? And then people talk about different pathways, right? So you have a pathway about the where, which is about the localization of the sounds, and a pathway for the what, to know what kind of sound you're hearing, okay? Good. Now, before moving on, I will try to show you something. So I hope things are not gonna crash. If they do, sorry about that in advance, okay? So now I will share my right desktop. There you go. This is you. Okay. Do you see my desktop? Good. It's already working a little bit. Please don't crash. Please don't crash. Please don't crash. Okay. So what I'm gonna try to do. Okay, it's not crashing. This is great. What I'm gonna try to do now is to show you how sounds work. Okay, so first of all, do you know the relationship between the pitch and the frequency? Do you know what the frequency of sounds is? Anyone?
Well, it's the hertz, it's the wave, it does basically work.
Exactly. So the frequency, the amount of vibration of the pressure of the air will determine the pitch of the sound that you perceive. The more it vibrates, the higher the pitch will be. The lower it vibrates, the lower the pitch will be. All right? So here's my beautiful voice. There you go. So all these things that you see, these are all frequencies, right? So you see down here the number of the frequency. This is 100 hertz. This is 1,000 hertz. This is 2,000 hertz, and so on and so forth. So you see that the most, I mean, now I have a very beautiful microphone, so it's capturing a lot of frequencies, right? But we can play a little bit like this. For instance, we can isolate some of these frequencies, right? And now you see that the down I move, the lower the pitch of the voice becomes. And then if I move it higher, higher and higher, you're just gonna hear the little whisper of my voice like this, right? So as you can probably guess, the most important frequency for our voice are between 1,000 and 2,000 hertz, right? More or less. Good. Now, I have told you that the pitch is mapped onto frequencies, right? So what is the pitch? You can think of a pitch as a musical note, okay? So for instance, let's take a sine wave now, which is basically a wave vibrating. I mean, you cannot see it, right? So it's like this right here, and I'm gonna play a C. And you see the peak of this sound is at about 500 hertz, right? Now, I haven't checked that, but you can check it on Google, exactly what is the frequency of C, of central C, should be around 500 hertz, right? Now, the nice thing is that if I go up with my notes, you see the pitch is moving, right? Now, if you know a little bit about music, you might recall that this is called octave. You're moving up by an octave, right?
Are you also playing the notes because we cannot hear anything?
Oh, really?
Yeah.
That's bad. Oh, that's very bad.
Oh, never mind.
That's weird though. So let me try to fix this. Sorry about this. Oh my God. I'm so wrong. Why are you doing this to me? Now, you're gonna hear it, right?
Yeah, yeah.
Awesome. Sorry about that. I selected the wrong microphone. Okay, so back to it again. This is a C, right? Central C. It's about 500 hertz. Now, if you move up, you see that the frequency now, and you hear them, right, are moving up, and higher frequency give you a higher pitch. Now, if you know a little bit about music, this is an octave, right? So it's the same note, it's C, but shifted an octave higher, right? So you have these are forces. Now you see that the distance between these guys is the same, right? Why is it the case? Because this scale here is logarithmic. In the real world, the distance, the difference in vibration between one sound and an octave higher is exactly double. So if we take our main C, which is about 500 hertz, then we move it an octave up, this is going to be about 1000. Okay? Now, if you don't trust me, in particular 1.1, so it's 550. Okay? Now, if you don't trust me, we can play a trick and exclude these move away, move around, and only consider these little frequencies in the window that you see. And you see that when we get to the right frequency, we are going to hear a sound. And then when we move away, we don't hear anything anymore. Okay? If we take a major C chord, you see, this is G, this is E, this is C, and you can move around them. You finally hear the chord. Maybe I'm destroying your ear. Sorry, I realize the volume is a little bit higher. Okay? So the sound that I'm using is very pure. It's a sine wave. But I can, for instance, I can play an harp, which is nicer. All right? So one thing that you see, if I just play one note of the harp, is that you have a lot of stuff going on. You don't have one single peak as before, right? You have a lot of other things. Why? Because in reality, sounds are more complex. Especially, they have a lot of additional frequencies, which are called harmonics, okay? And that's what they make sounds so nice and so pleasant to hear. So for instance, this is called main formant, right? And if we isolate, that gives the note of this harp. But what is this one? This is an octave up formant, right? This is probably another octave. Octave, octave. This is not an octave anymore. This is a 7, okay? So, and you can play the same trick with my voice as well. So for instance, this is again my voice. I can try to sing something for you like do, right? Do. This is my C, assuming that it's a C. But then if I move a little bit here, do, you see that this is a different pitch, right? I'm not making any different note. It's just an harmonic that is present in my voice. And you see there are a lot of harmonics in our voice. So okay. So the interesting thing is that our hearing system is able to process all this frequency at the same time, to integrate the information about this frequency and to use it, for instance, to figure out whether the sound you're hearing is a lion that wants to eat you or a mosquito that you should kill and stuff like this. So very important for evolutionary purpose. Now, the question is, what happens if I take the pitch information away from my voice? Do you think you're going to be able to understand what I say? Yes or no? Well, let's try.
Can you understand what I say? Do you know? I will exterminate the human population very soon.
Sounds like a horror movie, right? By judging by your smile, I think you actually understood what I was saying. Now, this is a fancy experiment, a fancy exercise, but it's very relevant to what we are going to do, because that's actually what some people did. They eliminated the information of the pitch from the voice to try to see which area of the brains are sensitive to the pitch and which area of the brains are sensitive to other stuff, okay? Good. I think this is it for our little demonstration. Is there any question about this? Anything that is not clear? Is this clear? All good.
What do you mean by removing the pitch?
Yeah, good question. So basically, you see that now again, so now I'm just enhancing the frequencies, right, at different levels. So here's my pitch, and if I sing something, oh, and I move up and down, you hear all the different harmonics. Now I'm gonna.
And now you see.
You don't have any original information that is present in the original signal about the pitch when I turn the vocoder on. So if I do like this, you can still understand my speech, right? And you can see that the information about the tones is present in my voice.
But if I turn the vocoder on, now you understand a little bit. So as I
So if I understand it correctly, then what happens acoustically is that the main frequencies are increased so that you have the same level of acoustic energy at every harmonic.
Yeah, I mean, I don't know exactly how it works at the computational level, but basically this is a noise generator, right? And all the noise generators basically do not carry the information about a specific tone. So you have this kind of diffuse thing. And if you look at
what happens here,
as you're saying, it's kind of smoothing out all the information about different frequencies. And it gives you like this kind of wind sound like generator, okay? But you can still understand a little bit what I say, right?
Thereby masking the basic frequency.
Yeah. So, right. So some information about the variation of the frequency in the sound, you have it, but it's not the information about the tone, right? If I do like si, la, 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 la. I mean, still you see a little bit of frequency moving up and down here, but you cannot really hear any tonal information, okay? Good. Okay, so enough of this. Nice. So I would take a little break now because I need to restart my computer, okay? So let's take 5 minutes break and then we're not gonna take any more break. Okay, thank you. See you later. Okay.